Hello everyone, and my green screen isn't working. Hold on. Well, anyway, hello everyone and welcome to another stream here, and I hope that fixes the green screen. Yes, it does. Yes, we are gonna have another lesson today for live, and that means yeah, we have, this is gonna be the last one. And somebody's watching. Oh, that's me. Yeah, I watch myself on YouTube now, just in case there's an error on the stream, and I can see it immediately and fix it. So anyway, yeah, we have a lesson today, and we have IBDP physics today, yeah, and we're reviewing again for the exam coming up in 2 days. All right, I think the students already on the way in, sending over some problems to work on. 1, 2, 3, 4, 5. All right, let's get that open, and let's also share my screen, both on the classroom and here in the studio. Let's get to the board right away here. All right. Okay, let's see what the problems are first. Okay. Okay, we have a momentum question. Spring. That's that. Okay, we have that, and then it's part of that. Hello and good day. How's everything, Geeta?
Good. How about you?
Doing good. Doing good. Thanks for asking. All right. You sent me over a few, 5 questions or five images here. All right. So let's start then. Okay. So, okay. Where do we start? Okay, I think we'll start with this problem. We'll start first with the asteroid problem. Okay. Let me just see the rest of this. Yeah, this is pretty straightforward for the asteroid problem. Okay, so okay, gotta ask you now. So which one of these is giving you trouble?
Both.
Both these parts. All right then. Okay, it's actually relatively easy to do this. Okay. Okay, it's a head-on collision, and then it gets embedded on Earth. It says that right there, right? So you can say here that this is a totally inelastic collision. Totally inelastic collision. Inelastic, okay? So that means they stick together, right? So it doesn't really matter though whether we're doing this with elastic or partially elastic or totally inelastic collisions. Conservation of momentum will always be done, okay? So in this case, it says there that their speeds are equal but opposite, right? Or the velocities are equal but opposite. So let's put that in here. So here, this is the initial momentum. So P of the Earth here should be equal to, it says here that the mass of the Earth is M, right? And then V. Similarly here for the asteroid, the momentum of the asteroid would be small m V, right? But negative because of the opposite direction, right? Opposite direction thing. Now we have that, and then we have to draw again whenever we have conservation of momentum. We have to do the after collision, right? So we're going to say that the Earth asteroid system is gonna move at some direction like this, and we'll call that the speed or the velocity u, right there. Okay. In this case, the mass here would be the sum of the two masses, right? So what's the momentum here at the end? This will be the final momentum here would be m plus m, the two masses put together, times v, right? So what do we do? Sorry, not v. This is going to be u, right? And remember, for conservation of momentum, when you add this should be equal to that. So we get, so that's basically what we get. mv minus mv equals small, you can do big M first, because we're just adding, plus small m u. What do we do here? The v can be factored out, and that leaves us m minus m here. Okay, and then from there, it's just a matter of simple algebra, moving stuff around. Okay?
Yeah.
All right, so that's the first part. So again, the key here is two things. It says here embedded, so they are now moving together. And momentum is always conserved in this case. Okay? All right, so let's take a look here now. It's got this kinetic energy of 2.5 times 10 to the 25 joules. That's a large amount of energy. It doesn't tell us though what the actual speed is, right? Okay. Now, the reason for that is because we actually don't need the speed equation. This is in the data booklet. We will use the other one, the other equation for kinetic energy. That's p squared all over 2m. That's it. Okay. So show that the mass, so in this case, the mass will just move stuff around. That's going to be p squared over 2 times the kinetic energy, right? Okay. In this case, we know what the kinetic energy is. Do we know the momentum before impact? Let's see. That's going to be a problem.
We have that radius of the orbit.
Oh, it was given earlier, right? It was given earlier.
Yeah.
All right. So all we have to do now, what was given again earlier? Oh, sorry.
The radius, the Earth was in orbit, so it had a radius of 30 kilometers.
So the radius is 30 kilometers. What else? The radius of orbit, right? Okay. Is that gonna work? Is that gonna be useful? Radius of orbit. Okay. Yeah, we can, because from here
oh wait, sorry.
yeah, go ahead.
Sorry. Actually, the radius was 1.5 times 10 to the 11, and then the speed was 30 kilometers
Okay,
per
speed is given. Speed is equal to 30 kilometers per hour or per second?
second.
Per second. And the radius again was how many kilometers?
1.5, 1.5
1.5,
7,
10 to the 7,
10 to 11.
11 meters, right?
Yes.
Okay. Um, is that gonna be useful at the moment? I think it will be. So, let's just double check everything here. Is this locked yet? Yeah. All right. So I'll erase this first because we now have some information that we can use, right? If that's given, that makes it easier because what are we looking for? The mass, right? So since we're looking for the mass, we now use the other form, k equals 1/2 mv squared, because you're given the speed right here, right? So from here, the mass should be equal to the kinetic energy times 2 divided by the v squared. So kinetic energy is that times 2, that gives us 4 times 10 to the 25 divided by v, but this has to be 30 10 to the 3, that's 3.0 times 10 to the 4 meters per second, right? Okay. Is that correct? 3, yeah, that's correct. So if we put that in there, this gives us 9.0 times 10 to the 8. Okay, and this is now gonna give us the mass. So 4 to the 25 divided by 9 to the 8. Let's put that calculator. 4 exponent 25. Divide that by 9 exponent 8. That's it. Let's put that in scientific notation. Okay, that's 4.44 times 10 to the 16. 4.44 times 10 to the 16 kilograms. It's going to be a massive one, of course. That makes sense. But compared to the Earth, if I recall right, the Earth has a mass of magnitude 10 to the 30. I could verify that's just from memory. But either way, that's a big mass compared to 10 to the 16. Okay? So, all right. Then the last one here. The mass of the Earth is given here. Do we need to go through this one? I think so.
Yeah, can we go through it?
All right. Okay, so okay, I was wrong. It's 10 to the 24, but still a much more massive mass for the Earth, right? So after the collision, the Earth stays in a circular orbit. Assume that, right? Now, is this gonna be smaller or bigger? Think about it first. Did the suggest with the reason whether this would be increase or decrease. Now, what happened to the overall energy of the Earth? And then from there, you can determine whether it has enough energy to go farther or closer to the sun. Okay. Fastest. Let me just think of the fastest way to do it right now. Or the easiest. Let's not go for the fastest in this case. Let's go for the easiest. Okay. First of all, what's the answer here? Let me think again. Give me a moment. Okay. So just with the reason whether the new orbit will increase or decrease. All right. I think we better just solve this real quick. Okay. So there is an equation again in the data booklet relating the orbital speed and the orbital radius, right?
Yeah.
Okay. Okay, let me just check out what exactly it is. Because that's again one of the formulas I don't really memorize, so I gotta check. Okay. Here we go. Gravity, that should be in fields, which is topic D. Let's go to gravitational fields. Gravitational potential. No, not that. Not that. Okay, orbital velocity. We have the formula for the orbital velocity. Square root of gm over r. Okay. All right, so that's the equation. So from here, we can rearrange this to find the radius, right? So we square everything. We basically get r. R would be equal to gm over v orbitals squared, right? So from here, we know the Earth slows down because of the collision. Slightly, but it slows down, right?
Yep.
Slows down. Then from here, because it slows down, its orbital speed goes down, so that means r increases from the equation. Okay. Okay, so that's gonna be a real good trick for you to use if you have no idea how to solve it. At least look at the topic and then look for something that would look for an equation that would involve one of those two things being asked. Okay, the trick here, even though this was already in my head. Oh, sorry. Go ahead.
What would you say would happen to the total energy?
The total energy would stay the same, more or less. Okay. The reason is the Earth has its own kinetic energy. The asteroid had its own kinetic energy as well, but they also had their own gravitational energies, right? So adding all of those together, and if you just look at the Earth, asteroid, and sun system, if it's just those three, then the energy of the Earth and the asteroid relative to the sun must stay the same, right? So what could happen is the kinetic energy will decrease, the potential energy decreases. Okay? But the overall energy
It decreases
changes
as it moves away from Earth.
Yes. And then we know that the gravitational energy, the formula for gravitational energy for orbital stuff has a negative sign to it. Right?
Yeah.
The R becomes bigger in that case because it becomes closer to zero. Okay? All right. So anyway, the Earth slows down and R increases.
Sorry.
Go ahead. Go ahead.
If a potential energy decreases, like it becomes more negative, and kinetic energy decreases, then shouldn't it decrease overall?
Actually, it's the opposite. It's the other way around. If it increases, it should become more positive. So the GPE, the gravitational energy, once it increases, it should increase. It should become more positive. So it's like saying, if you start from -1 and then you go to 0, you increase from -1 to 0, right? Now, similarly, if you start from -2 and then you go to -1, that's still an increase. It gets the magnitude becomes smaller, but it actually increases. Okay.
Okay.
All right. So it's the same idea here later on. So this is one possible approach. The other possible approach is energy, as we said, right? So we'll just note that here. We have energy is conserved. Energy must be conserved. Okay. So that means since KE decreases, right? Decreases, the gravitational potential and energy must increase. And for this to happen, R increases. So one of these solutions would work. Either one, actually, of those solutions should work. All right. Any other question here?
But why does GP have to increase?
Because it's conserved. Because of this part, energy must be conserved. Okay, if it wasn't conserved, then okay, no problem. We don't have to think about energies anymore.
Okay.
Okay. Why is it conserved? Because basically, the only energies in there are gravitational energy and kinetic energy, and both of those are conservative forces. Okay.
Right.
Sorry, not forces, energies that would would be conserved. There's no friction, there's nothing else that would remove energy from the system, so to speak. Okay.
Okay.
All right,
Yeah.
let's move on to the next one then. So we're okay here, right?
Yeah.
Okay, let's see. You have sent a photo that, well, 3 photos for the same problem. Let's start with we're now doing the spring one. Okay, this is still momentum. Now, when I read the one with the spring, this is still actually about momentum. But this time, this now has either forces or energy built into the problem. Okay. All right, so let's move on. So that's the setup. So you have the bullet hitting a mass, right? And then the mass is attached to a spring. Okay. Now, I'm gonna tell you this much already. I'm already thinking the fastest way to do this is energy. Okay. Whenever you see a spring, and then you see different kinds of energy in there, energy is gonna be the fastest way. I already see spring, that's elastic energy. I already see kinetic energy in the here, right?
Yeah.
Okay, so in this case, that's what we use to find the maximum compression, because we know, let's do the before and after. What's the energy here? It's all 1/2 u m small u times small u squared. That's all the energy here, right? Then after the collision, what does it say here? After the collision, the block gets embedded, and then it's on a frictionless table, and then you're going for the maximum compression here. So maximum compression means it's already stopped, right? So in this case, there's the spring. This is the block. But remember that the block has the bullet inside it, right? So that's gonna be our compression there, x max, right? And in this case, v equals 0. So so that's what we use here. So in this case, we already have our energy here. Our energy here would be 1/2 kx squared. Okay, and therefore we can just equate the two. 1/2 mv squared equals 1/2 kx squared. Solve for k. The 1/2 cancels out. We're left with k is equal to mv squared over x, right? Okay, that's, however, all right, so that's other way. Sorry, let's do x here rather, right? So x squared would be equal to mv squared over k, right? Oh, hold on. I missed something. I knew I was missing something. Hold on. This is also involves a collision, right? So, okay. So let's lock that. There's an in-between step. Okay, the in-between step is the spring is still uncompressed, but the block and the bullet are now together, right? So this is gonna be u squared here, and let's now assume that this is gonna be v, moving at v, right? Okay, if that's moving at v, this has a combined mass of m plus m. Okay, so okay, that's why it's 3 steps. Let's erase everything again. Okay, so the idea now is we're gonna start with this and this. This has a momentum mu, right? So our momentum here on this step is gonna be m plus m times v, right? So we can now say what v is. So first of all, we do small mu. That's going to be equal to the sum of the masses times v. So we can get here that v is equal to small m over m plus m times u. Okay, so that's our v. Then we go here. This has a, in the other one here, so we do the same thing. What's the kinetic energy at this point? This is gonna be 1/2, then the combined mass m plus m times v squared, right? So in the first part, we went for conservation of momentum. Then on the second part, we go for conservation of energy. Okay. All right. So what do we do here? We do now 1/2 combined mass times velocity. Our velocity though is m over m plus mu, but you square that, right? And that's gonna be equal to 1/2 kx squared. So from here we move stuff around. And this m plus m cancels out with 1 because of the squared here. We're still left with 1 m plus m, right? So we're left with, what else cancels out? This 1/2 cancels out. We're looking for x. So here x will just be equal to, well, do x squared first. X squared will be equal to m squared u squared all over, this is left over m plus m, and then we have the k, and we already got it. Okay, so from here you finally get x is, we take the square root of everything, mu divided by combined mass times the spring constant, salt. Okay, so again, it's this problem, actually, if you're familiar with how to do this problem, with these kinds of problems, it's going to be easy. The challenge is to be familiar with this problem. Okay.
Yeah.
All right. But again, there are always 3 steps to this problem. First one's conservation of momentum. Second one is conservation of energy. Okay. All right. So we're given the values for the masses and the k, right? And we're looking for the maximum compression also given. So we're looking for speed u. So we just rearrange our equation from before. Here, we just move everything to the other side, right? So what do we get? Since we want u, so u will be equal to xk, sorry, forgot the square root here. X times the square root of k times the sum of the masses divided by u, m, small m, right? Okay, now we're gonna put everything in here since everything is given. So that's going to be equal to, compression is 9.4, centi is minus 2 meters, times k is square root of 390 times combined mass. That's going to be 5.022, right? Then divide the whole thing by the small mass, 0.022. Okay, so put that in the calculator. What do we get? Let's try that. 9.4 exponent -2, then divide by 0.022, then what's next? Then times this. What's this? 390 times 5.022, then take, you know what, okay, that kind of messed up in the calculator. Let's do it again. 390 times 5.022. Let's start with this. Take the square root times 9.4 exponent -2. Then finally divide by 0.022. So we're left with the speed u is equal to 1.89 meters per second. Oh, 1.89 1.89 times 10 squared meters per second, 189 meters per second. Okay, that makes sense for a slow bullet, so it's okay.
Okay.
All right. Okay, so everything clear so far? It's just really the math from here now, right?
Yeah.
All right. You still want to do D? I think you do, just in case, right?
Yeah.
Yeah.
If we can.
All right. So specific heat capacity of the bullet is this, and then estimate the loss of mechanical energy of the bullet. Well, we know U, we know V, right? We're given no, we don't know V yet. We don't know the speed of the bullet just yet. Oh, actually, yes, we do. It stops, right? Okay. So we know U is gonna be this 1.89. Oh, let's just say 189, right? 189 meters per second. V equals 0 because it's at the point where the bullet stops with the block when the spring rather is fully compressed. So that's that, right? So what's gonna be the change in the um energy here? And we're just looking at mechanical energy, so we're just looking kinetic and potential. But potential energy, it didn't really move up or down, so that's 0, right? So we'll just put it here. The change in the gravitational potential energy is 0. And then therefore, this is just gonna be equal to 1/2 mass times the change in the speeds. 0 squared minus 189 squared. Now, it's okay to have a negative answer here because we're looking at the difference. We're not looking at the actual energy, the actual kinetic energies. We're just looking at the difference. Okay? So from here, just put the values in the calculator. We square this. And then, what's the mass of the bullet? 22 grams. So times 0.022. And then, divided by 2. That gives us change in the energy here is equal to 3.93 times 10 squared joules. That's how much energy the bullet lost, more or less. Okay.
And why are we given the specific heat capacity?
I think it's for the next bit for part 2, but it's not here. I think I think it's a good idea to send that over because part 3 is given, right? Okay. You have it? Part 2?
Yeah, I have to find it. 1 second.
All right. So while you're doing that, I'll just put part 3 up on the next bit. Okay. Anyway, I think for part 2, because you're given the specific heat energy, it's gonna ask you for the change in the temperature of the bullet.
Right.
Okay. Just tell me whether that's correct, and then we'll solve it from here. You don't have to send me the image. Just tell me if that's the question.
Yeah, so the increase in temperature of the bullet is if all the energy and I goes
Okay.
into the internal energy of the bullet.
So part 2, we're assuming what's a change in temperature, assuming perfect transfer, right?
Yeah.
That's basically what it says. So let's just do it like that. Perfect transfer to internal energy. Okay. Okay. Energy. All right. That's gonna be easy now because we now know this energy, the energy loss, right? The next thing is, since that's all gonna be transferred, that's gonna be your Q. So that's gonna be what's the formula here? Q equals mc delta T. So so from here, delta T is just equal to Q over mc, and that's our Q. 3.9. Let's just use 393 joules divided by 0.022 grams kilograms times C is given, which was what was it? 320. Okay, 320 joules per kilogram per Kelvin, right? Is that Kelvin or degrees Celsius? Kelvin. All right, great. So in this case, our change in temperature will be expressed in kelvins, and that would just give us, put that back in the calculator, 393 divided by 0.022 and divided by 320. So our change in temperature would be 55. So delta T would be 5.9. Kelvin. Okay, now one trick here, and I want to mention this just in case this would be helpful. This is also going to be 55.9 degrees Celsius. Okay, because it's a change in temperature. So if temperature itself, temperature in Kelvin would be the temperature in degrees Celsius plus 273, right?
Yep.
0.15. So if it's temperature straight away, but if you have a temperature difference, okay, if you have a temperature difference, then the change in the temperature in Kelvin should be equal to the difference in the temperature in degrees Celsius. Doesn't matter. Okay. So here's the thing, and this is a personal pet peeve of mine. I've seen a lot of science books, but not really science textbooks, which make this mistake. Some of them convert a change in temperature to degrees Celsius by adding the 273. Okay, so be careful with that. Okay, so again, changes, there's no difference between degrees Celsius and Kelvin. Okay, all right,
And
go ahead.
just one before this question, there's a question that says it oscillates in simple harmonic motion, and how do we find the time, the period of the motion?
All right. What else is given? Because this is already simple harmonic motion, you already are given the equation here, right?
We're giving that after.
Oh, after. So the diagram shows the position at t equals 0. Positive displacements are to the right. State these values. Okay, you have to go back to the data booklet to make this easier. Okay, a simple harmonic motion would be topic C. Is that in? Yeah, you're gonna use the HL versions of the formulas. Okay. All right, so let's put all the equations we need here first, and then let's pick which one is best. Okay, so from here, let's shrink that a bit. Okay, which one seems promising? Because we want to find x0, we want to find omega, and we want to find phi, right? So let's take a look first. This is definitely promising, right?
Yeah.
Okay. Because that's exactly what's given to you anyway. Is there anything else that's promising?
But if we have 3 unknown variables, how can we find them from one equation?
Well, here's the thing. You know the velocity of the object, right? You know how fast it is. We just calculated that in here. This part, right? We know we can find out what the velocity is because we were given u. We found it out here, right?
Yeah.
So let's do that bit by bit. So what is v? We know that the v here at that v here would be equal to let's go back here. M small m over the sum times u, right? Small m over the sum times u, and we know u. Let's just get the value again. What was the value we got? This 189. Okay, use 189 meters per second. Okay, and then what do? We put this here, and then this v we put in here. Okay, in this case x equals 0. That's the first thing we do. Okay, so if we do that, let's look at the values. What's v gonna be equal to? So let's start with that. So v would be equal to the mass 0.22 divided by 5.022 times 189. So let's put that in again to find the v. 189 divided by times 0.022, then divided by 5.022. Okay, makes sense because it's much smaller. It's gonna move at 0.8 0.3 meters per second. Okay, so that's the first part. We now know V, right? So what are we gonna do now? We can what's the easiest one to do? We can do this first. Okay, since we know our V, we do 0.83 will be equal to plus or minus omega. X0 is our, okay, in this case, this is the maximum. This is at equilibrium, right? Equilibrium position. So this is the trick now. Because this is in equilibrium position, x equals 0. Okay? So if we use this now, this equation, we get x0 minus x. x0 squared minus x, that's just going to be x0. Then square root of that, that's just going to be x0. Okay? And okay, so that's the first thing we know. Omega x0. Okay, so we have 0.83 meters per second. So that's the first thing. We don't know yet. We don't know quite yet what the actual omega is or what the actual x0 is, right? But actually, we know x0. Okay, we know x0 because it's the maximum compression. This. Okay. So.
But isn't x the amplitude?
It is. Remember, the spring, it gets, when the bullet hits the block moves until it stops. And when it stops, that's when the spring is compressed, maximum, right? So maximum compression, amplitude.
Oh, it's just a negative.
Yeah. So in this case, we don't know its value, but we have the formula. So mu over some k square root, right? Actually, it's already given here. Actually, no, we don't even have to solve. It's given right here. Maximum compression is 99.4 cm. Yeah? So, x0 is 9. So let's put this here now. X0 is equal to 9.4 cm. Okay, so all we have to do now is change this. And we have that answer, right? So that's gonna be times 0.094. Hold on, let's remove this. Okay. Is there anything else I missed? I think I'm missing that's it already, because square root and that stuff, right? So yeah, from here we just find omega. We'll use a positive value for it. Okay, so it's gonna be 0.83 over 0.094. Calculator. We'll divide this by 0.094, and that gives us 8.81. Okay, 8.81. This is already gonna be in radians per second. Okay, so we've found omega, we've found x0. All we gotta do now is put these values of omega and x0 into here. Okay, so how exactly do we do that? So let's just do 0 is equal to the amplitude 0.094. Sine of our omega is well, it doesn't really matter. Let's put it in there. 8.81 meters per 8.81. Our t is gonna be 0 plus phi. Now, why did I think you may have a question on how I got those values, right? Specifically, why is this 0?
Yeah.
Okay. I think the others are obvious. This is our equilibrium position, right? This is our displacement. This is our angular velocity. But why is the time 0? Because you're gonna start timing the oscillation when the bullet hits the block. T equals 0, it's right there in equilibrium position. So the reason here, T equals 0, X equals equilibrium. which we have set to be 0. So at. So that's the reason why the equation's that. So again, this is your x, and this part is your t. Okay.
Why do we choose x to be 0?
Because it's easiest to do that for simple harmonic oscillation. In SHM, you pick 0 to be the equilibrium position, then the two displacements will be negative from that, or positive from that. Okay?
Okay.
All right. So, start of compression, right? I'll just note it here. Compression. So at the start of the compression, t equals 0. It's at equilibrium, x equals 0. So, done. From here, we find phi. Okay? So, for this to be 0, then that means sine phi should be equal to 0 as well, right? Because the 0.094 cannot be 0. So, what's phi? What are possible values for phi? Let's just do calculator. My brain isn't braining totally right now. So, all right, clear everything. What's the inverse sine? It's also 0. Okay. Sine of 0 is 0. So, phi is equal to 0 as well. Okay.
So what happens to the 0.094 times the sine of that?
Sorry, say that again.
We had 0.094 times sine.
Oh, okay. Remember, the sine applies to the whole thing, right? But because this part is 0, then that means we can't really. Okay, so we can't really put these together because the sine goes with the whole thing here. Okay, so if we put brackets into it to make it easier to see, remember the bracketing would be something like this. Okay.
Okay.
Okay. Okay. Anything else you'd like to ask?
It's clear.
All right. There's one more possibility. Remember, if we're doing in physics, this is good enough. Okay, in physics, this is good enough. But in math, I just want to go there. If this was done in math, this could be pi, 2 pi, 3 pi, then positive or negative, positive or negative, positive, negative, and so on. Okay?
Yeah.
But in physics, 0 is good enough. We're good there. All right. Okay, let's move on. How many more questions do we need to go through? Okay.
That's one that I mentioned from before, but it's a different question.
Okay, you sent me 3 more. Okay, let's do the graph problem, the one with radioactivity. Okay.
Okay.
All right. Radioactivity. So you have a pure sample, and it contains that many nuclei, and then it decays from X to Y, correct? And then we have this graph given here. The half-life of X for part A should be easy to get, right?
Yeah, I have it.
Okay. You just go to the graph, go to 5 on the graph because you start off at 10. Well, not exactly 10. You start off at 9, right? So you should go at around 4.5. So 5 would be here, 4.5 would be here. So half-life would be 0.6. Okay. Now let's go to your actual question. Suggest how it may be deduced that Y is either stable or has a very long half-life. Okay, let's take a look at some information, see if there's anything useful. I'm gonna guess. Okay. Right, that makes it easy actually. All right, you see here that the half-life of X is in minutes, right? Okay. If so, that's the hint. The half-life. Okay. Half-life of X is in minutes. So it's short, right? So I'm just gonna say short. Okay. Now, if the half-life of y is also short, then we shouldn't follow the same curve. It shouldn't increase like this. Okay. So since I'm just gonna write it here like this, since y keeps increasing, either it doesn't decay and it does not decay, which is stable, right? Or it decays very slowly.
But only 3 minutes passed, so it couldn't decay right after.
Now, think about it this way. This is gonna be more more visual if you think about this. Now, we know that X has like a half-life of 3 minutes, right? Is it? No, 0.6. So 0.6, like 30 seconds, around 30 seconds, right? But think about it this way. If Y also had a very short half-life, once you have a little bit, it should decay immediately. So let's say that after a few moments, it gets to this much. But after, let's say after 30 seconds again, it should also decay already. So in other words, you are producing more, but it's also decaying. And therefore, you should get somewhat of a curve like this. This is if Y was also radioactive. Yeah.
So the curve should be almost a straight line.
More or less a straight line. Because if it's radioactive, it would decay as it's being produced. And you wouldn't accumulate a lot, right? So either decay or long half-life, right? I'll just write it here. Half-life. Then I'll just write it with another color here. If short half-life, if Y's half-life is short, the graph should show, I'll just write it here, graph should show a decaying a decaying graph as well. Okay.
And can we find the half-life of Y?
At this point, no, we cannot. We need to graph Y's decay curve separately from X. That's what it's saying here. Yeah. But yeah, I know this is tricky because you don't really see this problem. When you see this problem here, you normally just think, okay, that's natural because Y will be produced as X decays. But the key idea here again is for Y to also increase, it must not be it must be either stable or has a long half-life. Because again, it should decay as it's being produced. Okay?
So we'd have to wait for the Y curve to decrease to find its half-life.
Yes. So in other words, what you could do is you can get a sample of Y and then observe it separately.
Okay.
All right. So it should be in isolation from X. Shouldn't be together. Okay. So determine the time at which the ratio is 2 for Y to X, right? So it should be easy. Let's assume it's stable. Let's assume that Y is stable. So let's write that here. Assume Y is stable. Okay, if it's stable, what do? We know that basically X turns into Y, right? But the amount of so let's kind of do it like, shall we do it mathematically? Yeah, there's an equation, right? For half-life, that should be under quantum mechanics, topic E. Here. Quantum radioactive decay. Here. All right. This is going to be our equation. we'll use the n equals n0 e raised to, actually no, that's not gonna be good. Do we know the activity? Yes, we do. We can get the activity from the graph, right? Okay, so what we'll do here, okay, we also know this, that the half-life is equal to natural logarithm of 2 divided by the half-life. So that's what we would get from the graph. Okay, so let's take a look. What's the half-life again of x? So what we'll do here is n. Let's do first an equation. So nx would be this, right? But what's ny? It's going to be n0 minus nx, right? Okay.
Why?
Because x turns to y. So how many particles of x you have, you should have that many particles of y. You start off with n0, right?
And n0 is the total of x.
Yeah, that's right.
Okay.
Okay. So what we're gonna do now is we're doing ny over nx, right? So ny over nx. That will be equal to n0 minus nx all over n0 e raised to negative lambda t, right? We're looking for the time wherein this is equal to 2. So we just do the math from here. Okay, so what do we get? And then this is just what we're gonna be looking at. So we get n0 minus nx should be equal to 2n0 e raised to negative lambda t. We might as well solve for lambda first. The half-life, according to our equation, was 0.6 seconds, right? Or 0.6 minutes, which is 36 seconds. Is it? So 9 to 4.5 is here. Yeah, 0.6, 36 seconds. So t1 half, let's put that here. Sorry, not that, but should be big T. T1 half is equal to 36 seconds. So the activity here will be calculator ln2 to find the natural logarithm. Where's ln here? Divided by 0.36. Divided by 36. So our lambda, our decay constant here is 1.93 times 10 to the minus 2. Okay. This is going to be per second. Okay, that's the decay constant. Okay, let's put that into the formula from here. Okay. Is there anything else we need to kind of know? Do we know the number of, do we need to know the n? Yeah, we do know nx. We do know nx. It's 9 times 10 to the 22. n0 rather, yeah? So since we know n0, we put that here. So 9 times 10 to the 22 minus nx should be equal to 18 times 10 to the 22 e raised to lambda t. Negative. Okay. Then from here, we just divide this by this. Actually, yeah, we just... What else? Oh, right. The nx is still n0 e to the minus lambda t, right? Okay. I think we'll do this like so first. Okay, I'll just keep this as nx first. I think that's gonna be faster. Then we change nx later. Okay. Nx there, right? So what are we left with? That's gonna be n0 over nx minus 1. That's easier. Equals 2, right? So n0 over nx is equal to 3. And now we put in our value for n0 earlier, which is the nx, this thing. The nx equals n0 e raised to that, okay? So n0 over n0 e minus lambda t equals 3. All right, that makes it easier. NO cancels out. We don't need NO. Okay, so from here, what do we get? 1/3 equals e raised to negative lambda t. And we can just rewrite that. We'll do a shortcut in math. That's e equals e lambda t, right? We know lambda. We can substitute it in later. So we just do ln of both sides, right? So ln 3 equals lambda t. And finally, t is found. T equals ln 3 over lambda. Now we do know lambda. We found the value. It's right here. So that's it. Okay.
Okay.
All right. Yeah, that's the fastest way. Honestly, I tried just to do it with brute mathematical thing, but just solve it straight away. But it's actually easier when we did it with algebra first. Yeah.
Yeah.
So if in this case, algebra first. All right. But aside from that, I think the solution's pretty straightforward from here on out. Questions?
No questions.
All right. Great. We still have 2 images, but we might as well go through it real quick. But okay, one is relativity, the other is relativity. What's your question? Well, the second one, you sent this problem again before, the rocket. So what's your question here?
Yeah, the question, we didn't go through t, and I don't understand why in the mark scheme we said that we find t with v over c squared.
So, okay.
And also, there was a question that we covered. It was which one the rocket sees first.
Mm-hmm.
And for some reason, when they drew the world lines, they picked the left one instead of the right one, and we picked the right one. And I don't understand, how do we know which world line we picked to decide which one intersects?
Oh, okay. You have to go into the... Okay, let's go to the world line first, because we've discussed that before, right? So,
Yeah.
instead of thinking first of the actual world lines, let's go into the reality, right? So here in this particular case, it's mentioned that the rocket is already somewhere between the 2 lines, between the 2 lights rather, right?
Exactly in the middle.
Exactly in the middle, at least relative to whom? Well, it doesn't matter. It's somewhere in the middle, right? So I think that's relative to S, not the rocket, but the spaceship or the space station, right? But either way, even if it's relative to the rocket, the idea is the rocket is still somewhere in between the 2 lights, right? So if we're gonna draw that, so if we draw the spaceship's coordinate system first, right? So if this is the spaceship, if this is the actual location of S, the light would be somewhere here, L1, right? But I'm not going to draw its position. Rather, I'm going to draw its possible trajectory along there, right? So this is going to be the L1 line, timeline, all right? L1 timeline. And then similarly, we'll do an L2 timeline. 1, 2, 3, 1, 2, 3. We'll do an L2 timeline here, right? Okay. And we also know, let's not even do the spaceship for now. We know that L2 happens after L1. So something like that. These points represent the times. We don't really know where the times exactly are, but it's going to be like that, right? And finally, let's draw the rocket's speed. So that's the rocket, right? So this is R. So this is going to be CT prime, and for now we'll skip the rest. Just these for now, right? Let's kind of draw the X prime line as well, just to make it easier to see where our proper angle, so to speak. This is our X prime. This is our X. This is our CT, right? Okay. So last thing we're going to draw are the two world lines from the lights. Okay, but this time we're gonna look at the possible world lines for the lights that would make sense in our problem. In our problem, if we draw this world line here, it doesn't make sense anymore for the line, because that light's not gonna go to R, right?
But in the Maxim, R did pass over L1 and they picked that line. So
Yeah, no, what I mean is this light, not this point, but this light. You get you get the idea? The light, this particular light, light cone, right, will not intersect R anymore. It will intersect, however, again, we're looking at this in S's reference frame first. S first. Okay. So in S's reference frame though, that's our world line there. So this light cone light here, or this light cone line, intersects CT. So that CT will, the rocket will see that. Okay. So not seen by rocket, not seen by R, right? Seen by R, right? Now I'm going to do another color just for this light cone here. Let's do this like that. So this is definitely, even though I drew that bad, let's just draw it more easily. Now in this case, this light ray is seen by R as well, right? Because it intersects the R. Seen by R, right? But similarly, if I'm going to, okay, what's gonna happen to this? Now, if you look at the CT graph, there's no way that this is gonna be seen, not seen by R, right? Because there's no way they're gonna intersect. So that's why we will disregard this. So disregard and disregard this one, because it's not gonna be predictive, at least for R. So once we draw the line for what are we gonna do? Same time. So we're gonna draw, so once we draw this X prime graph, oops, let's use a different color here again. Once we draw the X prime graph like so, and we draw its we draw like the which one does it meet first again? In this case, it happens simultaneously like that. Perfect. I just drew that really perfectly. In this case, they happen simultaneously. Okay.
Right.
For R. This happens simultaneously for R in this case. That is totally coincidental. I planned it to be not coincidental. I was trying to plan it so they wouldn't intersect, or they wouldn't happen at the same time for R. But it does. Okay?
Okay, I understand. Yeah.
Alright, got it? Okay, so that's... Okay, last question. We're a bit over time. Let's try if we can finish this last one in 5. Yeah?
Okay, very sorry.
No worries. Again, you're my only class right now. I'm bored.
Also, I wanted to ask what the name of your channel is again, so I can watch the video.
Here, Freaky Physics. I'll put it. Freaky Physics, YouTube. Okay.
Okay, thank you.
Okay. Now, here's the thing. I like saying this on the channel anyway. If call me out if I make a mistake. I'm okay with that. If I make a mistake, somebody calls me out, I will either try to explain again, or I'll see your point of view why I made a mistake. Then we'll go over it again either way, yeah?
Okay.
All right. So, anyway, let's take a look here. Which one of these questions would you like to be done? Because the graph isn't here.
Just I.
At part 3. Use T using a Lorentz transformation. This one, right?
And we know that V is 0.8 C.
Let's put that here. V equals 0.8 C. Okay. Okay. What else do we know? I think we've done this problem a little bit before. Let me see. Or something similar.
In the mark scheme, they used V over C2.
Ah.
So I
Okay.
don't understand where it comes from.
What? Say it again. V.
I don't understand. Yeah. T equals to V over C squared.
V over C squared. All right. Okay. Let's just do that again using the data booklet. Okay. So from the data booklet, again, let's look at the possible equations to use. So this is something you can actually try later on if you have no idea what to do and you have time to do it later on. Because, you know, if you don't know how to do it, just skip it first, right? Focus on the ones you can do. But once you have time to do the things you don't know, this is a technique which I think works if you don't know what to do exactly. Yeah. So the technique is you go to the data booklet, go to the relevant section, and start looking at the equations that actually would be useful. Okay, so let's do. Okay, here we go. Galilean special relativity. We have. So we'll do the trick. I'll show you how to do the trick. This actually worked for me a lot when we were doing physics in uni. So this worked. This works, more or less, if you have time. Yeah.
Okay.
Okay, so here are our formulas, and what we're gonna do is we're gonna try to look for which one is which. But here's the thing: we know that the first three are Galilean, so we'll skip these Galilean, right? Since we're doing special relativity and we need time, we can use either this or this, right? Or what else? We can also use this, or we can also use this. Now, which one seems easiest to apply?
Probably the last one.
Okay. The problem with doing the last time is it's looking for a time interval. Okay. Okay. Actually, what would be the best one to use? Because I need something else here. Okay, let me just check on the app. Yeah, because I'm pretty sure you sent me this problem before.
If I can send that again.
Just give me the like the graph part. Wait, I found it. Copy. Okay, never mind. I found it. So let's copy this again. And copy image. This is the exact same problem, right? So
Yeah.
okay, yeah, draw a dot, determine V, and determine T using Lorentz transformation. Okay, this is gonna be more useful. Let's put it here. And we know V is equal to 0.8. And there we go. It's the same one, right? Just double check. Yes, okay. So lock this. So what is T? Okay, so again, we need to know. Okay, so what's the Lorentz? Okay, we know that L1 should be somewhere here. We know that already, right? Should be somewhere there. What's our T? Our T is this interval here. Okay. Yeah, so this is gonna be equal to some delta T. So yeah, we are gonna use the delta T formula. Okay, so we're gonna use, yeah, this one. So you were right, we'll use that. Okay, our T0 is going to be hold on though, because it happens at the same time. We cannot use that because it happens at the same time in the rocket's point of view, right? So which one will not be 0? Okay, this This is gonna be useful. It's this one. Okay. Why? Because according to okay, let's do it like that. So t prime, let's write it down first. A gamma would be 1 over square root of 1 minus c squared, v squared over c squared. Then we have t minus v x over c squared, right? So if we go into the graph, we can actually find, where's the graph again? Hold on. Lorentz transformation. It's gonna be tricky because of the simultaneity thing. Oh, okay. So, if we do that, they're simultaneous. They're not simultaneous in here. We need to know this length. We need to know the length. Okay, I think we need to use the space-time interval equation here. What else is given? Try and indicate. We know how long the space station was, right?
120 meters. Sorry,
1,200. Okay, 1,200. So that's going to be 600 here and 600 on this side, right? Okay, is that useful? It is, because we know that our length is 1,200 and space-time interval. Okay, let's use that equation, the space-time interval equation. There. So delta S squared equals C delta T, but this doesn't use the Lorentz transformation, though, so I don't think this will be valid. Minus delta X squared, right? Okay. And this would be C delta T prime squared minus delta X prime squared. No, that won't work either. Okay. You know what? Okay, this is what I'll do. I'll put this on the channel. I'll skip streaming so that you can rest a bit. I need to figure this out real quick. And I don't want to keep you too much, okay?
Okay.
Alright, so I'll just...
I sent you a screenshot of something that might help.
Alright. So there may be something that I may need. Alright, so we'll just end today just on the stream. For the latest stream, I'll put this up here. I'll probably... I'll just tell you when it's ready, okay?
Okay.
Alright.
Thank you very much.
Alright, okay, so I'll see you. Good luck again on Tuesday.
Thank you.
Alright. Relax.
Okay.
You got it. You're sending me hard problems. You got this. Okay?
Okay.
Alright, so I'll see you soon. Yeah, bye now. You have a good day.
Bye. Have a good day.
Alright, so let's take a look here. So I'm gonna stay on the stream just because I want to finish this as well. Space-time diagram. Okay, the mark scheme says this, which, okay, that's correct. Okay. Alright, so I was actually on the way of doing that, but somehow the 0 is keeping me from doing anything. But, okay. Let's redo the whole thing. I'll just erase the whole thing now. I was overthinking this, and it will happen, especially when you're tired. So don't be too scared about, just trying stuff. When I'm not that tired, or when I'm not this tired, I am not afraid to just try. But this time, I don't know why. I'm sleepy. A bit sleepy. So, yeah. So, anyway, here's the idea. I'm not gonna put the mark scheme here on the stream, just to make it a bit easier for us to follow. Okay, but we're gonna start off with, again, the equations that we would start with. I actually already started with the correct equation. We need to start with this. Okay, now In this case, though, it's going to be, let's start with this, and then we're gonna have to, okay, this is the thing I was already thinking, and I'll just do it now. Okay, the idea now is we're gonna look for the time difference. So instead of saying t, we're gonna say delta t prime. Okay, now we will not follow this equation right here. Okay, we will not follow this delta t in the equation because that's for a very specific case. So we will just use this. Okay, so if we use that formula, so that's going to become, the gamma still gonna be gamma no matter what the time is. Okay, okay, I think it's better to show it long way first. So instead of saying delta t, we're gonna do t2 prime minus t1 prime. That's gonna be easier. Okay, so our t2, this is gonna be gamma t1 minus vx over c squared, like so, and then we're gonna subtract the one for t1. Oh, sorry, this should be t2 right there. Okay, it should be gamma t1 here, then minus vx over c squared. Okay, here's the thing though, the x also changes, so we're gonna have to label them 2 and 1 here. Okay, so the times would change, but the x's would also change. So this is going to be, of course, it's gonna be delta t prime. Now what can we do here? We can put the gamma in. We can put the gamma in and then solve individually. So what will happen is, if we put the gamma in, we're gonna get this t2 minus t1 like so. So that comes from these parts. Okay, and then we're gonna also do this part. So minus gamma vx1 over c squared, then minus minus. So that's gonna be a plus. So plus gamma vx2, sorry, this should be the 2 and this should be the 1 over c squared. Now the thing now is, we can now actually rewrite this. So I'm just gonna show you the proof first before we solve. T prime, this part is just t, delta t specifically, so that's gonna be gamma delta t. Now what can we factor out here? We can factor out the gamma v and c squared from these guys, and we're gonna keep the minus, so we're gonna keep this negative here, so we'll do gamma v over c squared. What's left? We have x2 minus x1, and that is just delta x. So that's how we would, this is going to be the better way to do it. We actually derive the difference in the times using the equation we get. Okay, and one more thing, we have gamma again on both sides. We'll just factor that out again. We get delta t minus v delta x all over c squared. Okay, so that's just the proof that we can do that. Now what do? We know that in the rocket, the events were simultaneous. So which one is going to be delta, which one's going to be zero here? Because our reference frame, our original reference frame was outside, it was the space station, t prime is for the rocket. So we know they happen at the same time. So delta t prime is 0, simultaneous in the rocket. So that's what we actually go for. So we are gonna do we're gonna get that 0 is equal to gamma times, excuse me, delta t minus v delta x over c squared. Now because of that, gamma cannot be 0, so this must be the 0 bit. So delta t is equal to v delta x all over c squared. And what's the thing? We know that delta t is the time difference, so that's going to be equal to the time difference in the problem. And now we have it. We have our v, we have our x, we have c squared. So what's our v? That's 0.8 c. Our delta x is 1,200 meters. Finally, our c squared is just c squared. One c here cancels with this c. So we're left with so we're now gonna do 0.8 times 1,200 divided by 3 times 10 to the 8. And there is our final solution. We'll just put that in the calculator. 0.8 times 1,200, then divide that by 3 exponent 8. That's gonna give us 3.2 times 10 to the minus 6. It's a period, so that's gonna be seconds. It's gonna be a time, so that's gonna be seconds. And yeah, that's the final answer there. Again, okay, hold on. Where is my mouse cursor? All right. So again, I know this bit is confusing. I'm like I said, these two are confusing. Okay. Just to be sure, remember this. Since we're comparing Galilean, sorry, not Galilean. We're comparing relativistic motion here. We just stay here. Okay. Now, I want to clarify what that other equation is. Okay. This other equation is still kind of related to this, but this is going to be the if you have two different clocks. In this case though, we have one single clock, so I guess that's one way for us to remember this. This is one clock in one reference frame. This is two clocks. Okay, so again, a bit tricky, so we need to really know the intricacies behind it, and for me, I'm gonna have to practice that a bit. So but either way, this is the safer option, so always use this. Well, not always, but use it for most calculations. If it's pretty obvious what the answer would be when you have two clocks, we'll do it like that. But for examples, I think I better show you an example later on. Okay, so that's the last bit there. Well, hate it or like it. Well, I see this on the screen. Hate it or like it, we're gonna do it. So might as well learn, right? Anyway, yeah, I just read that message over here. Okay, so anyway, so that's it. I will stop the stream here today. So hopefully that was the answer there. So before we go though, don't forget to like, share, subscribe to the channel again. We are on YouTube, Facebook, TikTok, Instagram, and on Twitch, whichever one you want to follow. I think I'll be dropping one of these soon, and focus. I'll be going live on some of these soon. I'll focus mostly on, yeah, but it doesn't really matter. Doesn't really matter. So I think but either way, I'll drop one of these probably, but we'll see. Okay, but anyway, going back, so we're on YouTube, Facebook, TikTok, Instagram, and on Twitch. And with that, we'll end our stream. So don't forget to like, share, and subscribe. And with that, of course, I bid you all a good morning, good day, good